Okay, the answers to problem set 4. Question 1, that's the gravitational force is also equal to the weight, so the same force is given in two different ways, which you can rearrange and calculate the mass of the Earth. .96 times 10 to the 24. Now to find the density, all you got to do is mass divided by the volume. The volume of a sphere is 4 by 3 pi r cubed. The 3 transfers to the top, and plug in the numbers. You get the answer as around, approximately, because I've not calculated, it should be about 5,500 kilogram per meter cube. That's the approximate answer. And question number 2, G is gm by r squared, that is acceleration due to gravity. Plug in the mass of the moon and the radius, and you get 1.6 meter per second squared. And question 3, acceleration due to gravity on the Earth, and this is on the planet. Divide one by the other. The constants cancel, and rearrange that. Since the masses are, the ratio of the masses is given as 1.66 and the radii are equal, plug the answers, the numbers, and get the answer as 16.26 meter per second squared. And number 4, again the acceleration due to gravity is gm by r squared, and the distance must be from the center, so you have to add the height to the radius. And both have to be in meters. You will get 9.75 meter per second squared. The second part, do the same thing, but this time the distance is 3,200 kilometers, so got to change it. Do the same thing and you will get the answers 4.34 meter per second squared. Question 5, you have those 4 spheres and you have to find the force on one of them. In this case, you know that the force on 3 due to 2 and that due to 4 are equal, because all quantities are equal, and that is given by G m1 m2. That's why you have 9.5 squared, and you get that. And then to find the force by 1 on 3, first find the distance as square root of 2 times the side, and then use the gravitation formula to find the force on 3 due to 1. Now, since that force is neither along the x nor y, it has to be resolved. And surely the two components are going to be equal because the angle is 45 degrees. As given by 124.9 G cos 45 degrees. So you have it as 88.32 G. So now you have the total x component equal to the total y component and will be 250.7 plus this component that we got now. So when you add it, you get 339. So now you have two components that have the same value, and so to find the result and square them, add them, and take the square root. So you get the magnitude of the force as 3.19 times 10 to the negative 8 newtons. And of course the direction is at 45 degrees to the x-axis or to the y. Number 6. The centripetal force in this case is the gravitational force. And so rearranging, you get the formula for the orbital velocity. So that's the velocity with which a satellite goes around a planet. Find the actual distance from the center of the satellite to the planet. And the answer is 7.881 kilometer per second. In question 7, the apparent weight is going to be the normal reaction. And in this case, the net force along the y-axis is mg minus fn is equal to 0. And the weight can be given by gmm by r squared. So plug in the masses of the moon and the astronaut and radius squared, and you get the apparent weight as 59.23. And that is because it was moving at constant velocity. There was no acceleration. Just remember that there's no acceleration. That's why this term was 0. But in the next case, it is moving towards the moon with an acceleration. So that's why on the right hand side you got to have the mass multiplied by the acceleration now. So that's the only difference. And you would get a negative force showing that the astronaut has a chance of going away from the seat or from the floor and needs safety belts to keep him down there. Okay, so those are some calculation mistakes that I made, and I've corrected it now. I think it's negative 197 Newton. And question 8. Once again, the gravitational force is the centripetal force. Make the velocity the subject, and you get gme by r, which is the formula for orbital velocity. But again, time period is circumference divided by velocity, because time is displacement by velocity. And now you can substitute, square both sides, and when you square both sides you get 4 pi squared r cube, because there is an r here which goes to the top, and this becomes r squared, and there's already r squared when you square it, and there's an r. So that's why you have an r cubed. This in itself is an important formula. And then you can find anything out of this, and if you want to find r cubed or r, make r cubed the subject. And because it's a geosynchronous satellite, it has the same time period as the Earth, which is 24 hours. Means it completes one rotation in 24 hours. And therefore, to find the radius, all you got to do is plug in all those numbers and take the cube root, which is essentially raising it to 1 by 3, which means you're taking the cube root, which gives you 4.23 times 10 to the 7 meter, which is the total distance. And therefore, if you have to find the height, you've got to take away the radius of the Earth. That gives 35.93 times 10 to the 6 meter. That's about 35,930 kilometers. That is the height of a geosynchronous satellite used for communication purposes.